Now, before going forward into the core aspects of inventory, I want to take some time and explain on this whiteboard the overall fluctuations in any inventory. So this can be, let's say, a large store, a large factory, or even a small coffee shop, etc. And essentially they would follow the same principles. So on my x-axis I have the days, and on my y-axis I have my stock, or SKU units, stock keeping units. So I will start off with setting a random value for the inventory, such as, let's say, 100 units on day one. So on day one we have, let's say, 100 units of stock for any stock items which we are storing, let's say, in the inventory. And let's say we have an average daily consumption or demand of 20 units per day. So essentially this level is going to drop off gradually by 20 units per day. So let's say I can plot a line showing the decrease at day 3, the level to be 60. So at this point now, we would generally have some sort of a reorder point or a safety stock, which would trigger based on when this level is reached. So let's say my reorder point is 60 units. And if you are using some sort of a inventory management system, this would typically involve generating a purchase order based on the details of the SKU or the item which we have created in our inventory system. And now let's say we are at day 4 and the level is at 40 units. So this can be, let's say, our safety stock level, so we should not go beyond this level based on our business requirements. And let's say the lead time is 1 day, so after placing an order we will be getting our deliveries on day 4. So in that case our inventory will get replenished at day 4 to a level of EOQ, or economic order quantity, or reorder quantity if you want to make it short. So let's say my ROQ was 160 and now the level has reached 200. So once again now, because of the ongoing continuous demand, let's say we are selling continuously the items in our stores. If it is a clothing store, we are selling the items on a daily basis at a demand to our customers. So this level is now going to decrease once again. So once again, once the level reaches the ROP level of 60, it's again going to generate the PO. And as I mentioned, this period is basically our lead time, and the demand during this period is actually called as lead time demand. So once again, let's say our lead time is 1 day and it reaches once again the level of 40 units, and once that is done it will replenish back the same amount of 200 units like the previous level. So in this lecture we looked at some of the core concepts of inventory, and you would be using them irrespective of any sort of business you operate. So starting with the reorder level, which we just looked at, reorder point of 60 for this particular scenario, and like we saw, after this is triggered it generates an order, and in duration of the lead time we would be consuming an inventory, but the idea is that in that duration, once it gets replenished, it will be replenished back to the reorder quantity, or EOQ. And then we looked at the lead time, which is this part here, the time it takes for suppliers to deliver our order, and lead time demand, which is basically your demand of inventory or the stock during that particular period, as well as the safety stock, which was this amount, and which is the minimum balance we must always maintain for our business to perform effectively. So these are some of the core concepts which we would be looking at in more detail, but a general point is that in the real world, because of the large variations across lead time and demand, the level of inventory would generally fluctuate. So for example, if you have your safety stock here, let's say there can be a scenario where you will be out of inventory and there will be something called as back orders, so you'd replenish more than EOQ, and then again there will be more variations in the levels, such as this might go up more than 200 and this might be gradually decreasing in something other than 20 units, which was the mean which we took as for a model. So there might be a scenario, let's say, where we are in a particular season that the demand is more, so this can increase, let's say, at a rate of 40, maybe at a faster rate, and then at a faster rate we'll hit our RFP and the safety stock. So in that case our levels will be impacted. So for example, and also there can be scenarios where this lead time is delayed because of some issues with supply, transportation, etc., etc. So those effects can come into the real from the real world and will impact our business. And looking back to our reorder quantity, or the EOQ, this particular metric is actually a balance between our holding cost and our purchase cost. So for example, we'll have the cost for the purchase orders which we are generating, the administrative cost and the cost of ordering, and the holding cost for this particular inventory. For example, we are holding, let's say, 200 units. So this ROQ is basically a balance between those two factors. That's why it is written as, let's say, the ratio of your holding cost and your ordering cost, and then we will multiply it with the factor of 2 times the demand. And this can be your let's say your daily demand, and then we will take a square root of this whole thing. And this is basically derived using calculus. We would basically find the point at which the total cost is minimized, but this is out of the scope of this lecture. But if you look at by intuition, we can see that it's basically striking a balance between the ordering cost and the holding cost, and basically it is factored on the demand itself. So if your demand is more, we'll obviously need to order more, and we'll also need to take into account the ratio of our ordering cost to the holding cost. So for example, if the holding cost is too large, we'll order less, and if the holding cost is on a lower side, we can order more because we can store more. And next, look at the lead time demand. So lead time demand is just the product of lead time and the demand. So basically it's just lead time demand is simply the product of lead time times demand. So for example, if the demand is, in this case, was 20 units per day and the lead time is 1 day, so that's just 20 units based on this relationship. And we have looked at the lead time demand. Now let's look at another concept called safety stock, which we identified here in this part. So safety stock is basically the stock you need to keep in order to guard off against the variation in lead time and demand. So what does that mean? Well, it basically means that we would take the lead time demand variance or standard deviation, and we would multiply it by a certain factor to prop up our inventory against the variance of lead time and demand. So it must be something like a constant, let's call it Z, times the lead time demand standard deviation, which is basically the square root of variance. So this factor Z is basically will be based on your service level, and what that means is that this is basically how much more confident you want to be in order to stock up your inventory. So typically this is based on a 95% confidence based on the Z value of the normal distribution, which we just discussed, and this value comes out to be roughly about 1.65. And the only thing you have to consider is that it's just a factor by which we increase this variance or the standard deviation of the lead time demand. So the whole concept is based around having sufficient safety stock based on the variance of the two main quantities, which is basically your lead time and demand. So essentially we can rewrite this as Z times variance of lead time times demand. So now how to understand this particular term of variance with respect to lead time and demand? Now, without going to too much mathematical details, I will just explain the general principle around variance. So variance of any two variables, so for example, let's say variance of x and y, and this essentially means how do both x and y vary together. So in case of x, for example, you saw during the normal distribution section that if the variance or standard deviation is high, the bell-shaped would be more flatter, for example, it would be more flatter, and the variance would be, let's say, will cause the bell curve to sort of flatten out. And when you apply this concept to two variables, we can write this relationship in terms of the mean and standard deviation of x as well as y. So once again, without going to too much math details, basically it's just we take the mean of x and we multiply it by the variance of the y term. So let's say this is y, and then we add the mean of the product of the mean of y times, let's say, the standard deviation of x. So we have the mean of x times the standard deviation of y plus the mean of y times the standard deviation of x, and basically we'll square these two terms. So we'll square this and we'll square this thing. So basically it becomes sort of like the mean x squared times variance, because variance is equal to standard deviation square. So basically it becomes the mean square of variance of like y plus mean square of y plus times the variance of so using this concept, basically what they do is for lead time demand variation, or let's say standard deviation, this will be equal to based on the variance of the lead time times demand mean plus, or let's just write it as mu of d plus the variance of demand times the mean of the lead time. And if you think of in a more intuitive way, basically we are taking how does the mean of lead time vary with the variation, or is impacted by the variation of the lead time, and vice versa. So this relationship overall becomes the two products of lead time with the standard deviation of demand plus demand squared plus times the lead time of the standard deviation of the lead time squared. And this whole relationship is actually based on this relationship which we just derived. And typically the demand is squared because in the actual formula it's basically the squaring of the mean, and lead time is not squared. So this particular relationship can then be used in our calculation of the safety stock.